last week we started answering the question about how, when you have two random variables x and y, how much information does y reveal about x? Does y reveal about x? And to answer this question, we noticed that we postulated that this question is actually the foundational question for statistical inference. So in statistical inference, there is an unknown. So there's an unknown, which is x for us. And for each value of this unknown, you observe something. So for each value of this unknown, this observed random variable y has different distribution. So the distribution of y condition on x is w of y, wx. This is the channel, or wx, when x takes the value of x. All right. So x is this unknown, and you observe y, and given a value of x, the distribution of y is wx. So this is the basic notion. This is the basic setting in statistical inference. Now there are various formulations which are popular in statistics. The first one is hypothesis testing, where different values of x correspond to your different hypotheses, and you want to look at y and figure out which of the hypotheses is true. The other formulation is estimation, where x can take possibly infinitely many values, and you observe y and you want to estimate x. Here, for estimation problem, you have to first agree on a loss function, and a typical loss function, the one we discussed last time, was expected mean square error. On the other hand, in hypothesis testing, the loss function, the criterion for goodness of a decision rule or a test, is the probability of error criterion. In fact, we saw two different variants of the hypothesis testing problem. We saw a Bayesian formulation, and we saw this Neiman Pearson formulation. Okay. So in Bayesian formulation, there is a prior belief on the probabilities with which x takes different values, and so we can think of example of binary hypothesis testing problem where there are only two hypotheses, and in this case the belief is about x taking the value 0 or x taking the value 1. These are two hypotheses. Sometimes the first one is called null hypothesis, the second one is called alternative hypothesis. Under both these hypotheses, y has different distributions, and we observe y and we want to figure out which of these hypotheses is true. So in Bayesian formulation, since we have probabilities on the prior on the values of x, a popular criterion to use is the average probability of error criterion, where average is based on this prior distribution on x. And what we saw was that the optimal rule for uniform prior, when you don't have any reason to prefer one hypothesis over other a priori, the optimal rule gives the minimum probability of error given by optimal rule is half into 1 minus total variation distance. So this is a very interesting formula. It brings out a very nice heuristic. What it tells us is that the probability of error is determined by this distance between the two distributions under the null and the alternative hypothesis, this total variation distance. So the closer the distributions, the harder it is to distinguish these two distributions. This is a very natural heuristic. Just like in measurements, the points which are closer are difficult to distinguish. You need a better scale to distinguish them. Similarly, hypotheses which are closer in this distance, total variation distance, are difficult to distinguish. Then we went to the Neiman-Pearson formulation. Now the criterion was slightly different. Now our goal was to minimize the probability of error of type 2. What was this probability of error of type 2? It was the probability that you declared 0 when the true hypothesis was 1. You declared null when the true hypothesis was the alternative hypothesis. So you want to minimize this probability of error of type 2 while keeping the probability of error of type 1 below epsilon. What is the probability of error of type 1? It is the probability that you declare 1 when the true hypothesis was 0. So once again, even in Neiman-Pearson formulation, the criterion is determined by these two different kind of probabilities of error. We were just taking average of these errors in Bayesian. Now we have a slightly different cost, we want one of them to be smaller than epsilon. It's sort of the less severe probability of error, and want to ensure that the more severe probability of error is minimized under this constraint. Okay. So what is the best criterion for Neiman Pearson formulation? Here we introduce this quantity we were calling beta epsilon W0 W1. Okay, this epsilon is the bound that you have for probability of error type 1. And we saw that we alluded to this thing called Stein's lemma. We said that when you have IID repetitions, when you have IID samples, then this probability of this beta epsilon, the minimum probability of error of type 2, given that probability of error of type 1 is less than epsilon, can be made to go to 0 exponentially rapidly. That's very fast. And it goes to 0 like 2 to the power minus n, the KL divergence between W0 and W1. So we essentially ended up discovering this new notion of distance called the KL divergence. Okay, and just like total variation distance determines the probability of error in the Bayesian case, KL divergence determines the probability of error for the Neiman-Pearson formulation. And we will see soon, as we go forward in this course, that this KL divergence is a more interesting notion for many applications than total variation distance. More interesting because it's more handy, and that's what we will discover slowly. So this week we'll continue with our discussion on statistics and information theory, and I will spend some time on the Emery hypothesis testing problem, not just the binary version that we saw in the first week. So I hope that you're enjoying these lectures. See you in the next lecture.